Have you ever been sitting at your computer and, you're juggling maybe a dozen browser tabs, compiling some huge chunk of code, streaming a video, chatting online, all at the same time? It feels like your machine is performing this incredible ballet, somehow managing everything effortlessly. But how does it actually do that? How does it make it all look so smooth?
It's a fantastic illusion, isn't it? What you're really experiencing there is the magic of the operating system. It's the silent orchestrator working behind the scenes for every single click, every program you launch, all the data you interact with.
Absolutely. And today, that's exactly what we're diving deep into, the very foundation of how your computer works. We're
Right.
going to unpack the really intricate world of process management, figure out how the OS juggles all those applications without, well, breaking a sweat. And then we'll pivot to something critical but often invisible: security. How does the OS keep your data safe? What are those hidden threats it's constantly fighting off?
Right. And our mission today is to really distill the key insights from a, frankly, comprehensive set of sources. We've got lots of insightful discussions on operating systems. We've got material covering everything from the basic building blocks like processes and memory,
Yeah.
all the way up to sophisticated scheduling algorithms and robust security measures. Think of this as your shortcut to getting genuinely well-informed about what makes your computer tick. Get ready for some surprising facts, maybe a few aha moments along the way.
Okay, let's start at the beginning. The absolute core. The operating system as an abstraction layer. That sounds kind of technical, maybe, but it's actually the unsung hero simplifying our digital lives, right?
Absolutely.
Yeah.
You could think of the OS as both a translator and a manager. It sits right in between the really complex hardware, all those circuits, memory chips, graphics cards, and the applications you actually use every day. Its main job, providing abstraction. Basically, it hides all the messy, low-level details of how the hardware works. This makes programming so much easier, and it also makes applications portable.
Okay, give us an example. That always helps it click. Like the classic Hello World program. Most people just type print Hello World and think that's it. Simple.
It seems simple, yeah. But under the hood, it's anything but trivial. For those two words to show up on your screen, the CPU needs to read that string from RAM byte by byte. Then it moves it into internal registers, maybe figures out the color, the exact coordinates on the screen, all sorts of display details. Then it has to talk to the graphics card hardware, passing all that info along so the graphics card can finally put the pixels on your monitor.
Wow. Okay, that's way more involved than I thought for just Hello World.
It really is.
Hmm.
And just imagine if every programmer had to write code to handle all of that every single time they wanted to display text. They'd need to know the specific memory addresses for the video buffer, the exact commands for that specific graphics card, what that specific monitor needs.
And your program would break if you swapped out your monitor or graphics card.
Almost certainly, yeah. So the OS steps in. It's the hero here. It abstracts away all those hardware specifics. When your program calls print, it's actually making what's called a system call. This tells the OS, hey, I need you to display this. The OS then takes over and does all the complex talking to the hardware, setting colors, positioning, communicating with the graphics card driver, all without the application needing to know any of the details.
And the benefits are huge then.
Definitely. Two big ones. First, reusability. Every single application using printf taps into one central OS module that handles screen output. Less code duplication, much more efficient. Second, and this is critical, portability. Because the OS handles those hardware differences, a program written using print can run on a desktop, a server, a laptop, maybe even some embedded device, without needing changes, as long as the OS is there to translate.
That makes perfect sense. So the OS hides the messy hardware stuff. But what's the basic thing it's managing? The fundamental unit it juggles? That's where processes come in, right? What exactly is a process?
Right. At its heart, a process is simply a program in execution. It's not just the code itself, though. It includes the program's current state, like what instruction it's on its resources, its whole execution environment. And crucially, each process is an isolated entity. It gets its own dedicated memory map.
Like its own private sandbox to play in.
Exactly like a sandbox. And that sandbox has a pretty standard structure. A typical process's memory map, its view of memory, is divided into sections. You've got the text segment, that's where the executable instructions, the actual program code, lives. Then there's the data segment, which holds global variables and static variables, things that exist for the whole program's life.
Okay, text and data. What else?
You also have the heap. This is for dynamically allocated memory. When you use functions like malloc and C to ask for memory while the program is running, it usually comes from the heap, which typically grows upwards in the address space. And going the other way, growing downwards, you have the stack. This is used for local variables within functions, for storing function call information, passing parameters, things that are temporary.
And there's a special zone just for the OS itself, kernel space.
Yes, and this is really key for security and control. A portion of every process's virtual address space, usually at the higher addresses, is reserved for the kernel space. This is where the operating system's own code and data live. The OS kernel has full access here, but user programs, they cannot directly touch this area. This separation is enforced by hardware privilege levels. The kernel runs at a higher privilege, maybe called Ring 0 on x86 systems, while user applications run at a lower privilege, like Ring 3. This gives the kernel ultimate control and protection.
So my web browser, running as a user process, can mess with its own text data heap stack. But it can't peek into the kernel's memory, or importantly, into another process's memory, like my online banking app.
That's the critical point.
Yeah.
Process isolation. It's absolutely fundamental for system stability and security. Each process lives in its own bubble, completely unaware of other processes running alongside it. This stops, for instance, some dodgy game you downloaded from snooping on your banking app's data. The OS acts as a strict gatekeeper, enforcing these boundaries.
Isolation equals security.
Got it.
But even with these isolated bubbles, memory, the actual RAM, is still finite. How does the OS manage that limited resource among all these competing processes?
Memory management is a huge challenge for the OS. RAM is limited, and you need to allocate it efficiently. One of the big headaches is fragmentation. As processes start up, run, and then exit, they leave holes in the physical RAM. Over time, the free memory can get broken up into lots of small, non-contiguous chunks. Individually, these chunks might be too small to fit a new process that needs, say, 1 megabyte, even if the total amount of free RAM adds up to way more than that.
So it's like having a lot of leftover scraps of fabric, but none are big enough to cut out the pattern you need.
Exactly. It's wasted space.
Mm.
To deal with this, operating systems use different allocating algorithms. Two classic ones are first fit and best fit. First fit is simple. The OS scans the list of free memory blocks and grabs the first one it finds that's big enough for the new process. Easy to implement, but it tends to create lots of small, leftover fragments, making fragmentation worse over time.
And best fit sounds, well, better.
It tries to be smarter, yeah. Best fit looks through all the free blocks and picks the one that's the closest fit, the smallest block that's still large enough. This usually leads to less wasted space within allocated blocks and potentially better overall utilization. The downside: performance. Scanning all the free blocks every time takes longer, so there's an overhead cost to finding that best fit.
Okay, so we have this core problem. Processes think they need one continuous chunk of memory, but the physical RAM often looks like Swiss cheese because of fragmentation. How does the OS bridge that gap?
This is where virtual memory and paging come in. It's a really elegant, fundamental concept in modern operating systems. The core idea is to decouple the process's view of memory from the physical layout of RAM. The OS divides the process's virtual address space, its logical view of memory, into fixed-sized chunks called pages. Typically, these are something like 4 kilobytes. Physical RAM is also divided into identically sized slots called page frames. The magic is that the pages of a single process don't need to be contiguous in physical RAM. Page 1 might be in frame 10, page 2 in frame 500, page 3 in frame 23. They can be scattered all over.
Whoa. Okay, so my program thinks it has this nice, neat, continuous block of memory addresses, maybe from 0 up to whatever it needs.
Right, that's its virtual address space.
But the OS is secretly mapping those virtual pages to physical page frames that could be anywhere in RAM. How on earth does it keep track of that mapping? That sounds complicated.
It uses page tables. Every process has its own page table, managed by the OS, usually stored in kernel space. This table is the crucial translation dictionary. For each virtual page the process uses, the page table holds the corresponding physical page frame number where that page actually lives in RAM. When the CPU tries to access a virtual address generated by your program, special hardware called the Memory Management Unit, MMU, uses the process's page table to look up the physical address before accessing RAM.
What if the page my program needs isn't currently in RAM? Maybe it got swapped out to disk. Does the program just crash?
Nope. That's another piece of the magic. Each entry in the page table has a special flag, often called the present bit. If this bit is off, it means the required page is not currently in physical RAM. When the MMU tries to access such a page, it triggers a hardware interrupt called a page fault trap. This immediately halts the user program and transfers control to the operating system. The OS page fault handler then figures out where the needed page is stored on disk, usually in a dedicated swap space or page file, finds a free page frame in RAM, potentially kicking out another page, loads the required page from disk into that frame, updates the page table entry, setting the present bit on, and then restarts the instruction that caused the fault. The user program resumes completely unaware that anything unusual just happened.
That's incredibly seamless from the program's perspective. But kicking another page out, how does the OS know if it needs to save the contents of that outgoing page back to disk first? Some pages might just be code, never changed, but others might hold data the program modified.
Great question. That's handled by another bit in the page table entry, the dirty bit, or modified bit. When a page is loaded into RAM, its dirty bit is initially off. If the process writes to that page at any point, the hardware automatically sets the dirty bit to 1. Later, if the OS decides to swap that page out, it checks the dirty bit. If it's 1, the OS knows the page has been modified and must be written back to the swap space on disk before the RAM frame can be reused. If the dirty bit is 0, the page hasn't changed since being loaded, so the OS can just discard the copy in RAM. The version on disk is still valid.
Clever. Saves unnecessary disk writes. And what about those protection bits you mentioned earlier?
Right, protection bits. These add another layer of security, also managed within the page table entries. They specify the allowed access types for each page, usually read, write, and execute permissions. So the OS can mark pages containing program code as read-only and execute-only. If the program accidentally or maliciously tries to write to a code page, the MMU will detect the violation based on the protection bits and trigger a different kind of fault, usually leading to the process being terminated, like a segmentation fault. This prevents self-modifying code bugs or certain types of attacks.
Okay, paging seems absolutely fundamental, but our sources also mention segmentation. How does that fit in? Is it totally separate, or does it work with paging?
It can be either, but often it works with paging. Segmentation is another way to manage memory, but instead of fixed-size pages, it divides memory into logical, variable-sized units called segments. These segments often correspond directly to logical parts of a program, like a code segment, a data segment, a stack segment.
So it's more about the meaning or purpose of the memory region rather than just fixed chunks.
Exactly. Some systems use segmentation as the primary mechanism. Others, like the BIV6 operating system often used for teaching, which our sources reference, use segmentation in a more minimal way, primarily for protection and setting up the basic memory model before paging takes over. For instance, BIV6 defines 4 main segments: kernel code, kernel data, user code, and user data. All these segments might actually start at virtual address 0 and cover the entire 4 GB address space, but they are assigned different privilege levels and segment types.
Privilege levels, that sounds like the ring 0 and ring 3 thing again.
It's directly related, yes. The segment descriptor includes a privilege level. DPL descriptor privilege level. DPL 0 is for the kernel, highest privilege. DPL 3 is for user processes, lowest privilege. Hardware checks ensure that code running at DPL 3 cannot directly access segments marked for DPL 0. Segment types also define permissions, like whether the segment is executable, readable, or writable. So even before paging, segmentation provides a coarse-grained protection mechanism. The address generated by the CPU goes through segmentation first, combining a segment selector and an offset to get a linear address, and then that linear address goes through the paging unit to get the final physical address.
All right, we've got the building blocks, processes with their isolated memory, managed through paging and maybe segmentation. Now let's get into how the OS actually conducts this orchestra. How does it manage the entire life of a process and decide who gets the spotlight to the CPU and when?
This is really where the OS acts like a busy stage manager. Processes aren't static, they transition through different states during their lifetime. It's a well-defined process lifecycle. When a process is first being created, it's in the new W state. Once the OS has done the setup and it's ready to compete for the CPU, it enters the ready state, waiting in a queue. When the OS scheduler picks it, it moves to the running state and executes instructions on the CPU.
What if it needs to wait for something, like me typing?
Right. If a running process needs to wait for an event like user input, data from the disk, or maybe a network packet, it transitions to the blockhead state, sometimes called waiting. It leaves the CPU and won't be considered for running again until that event occurs. Once the event happens, URECD data arrives from disk. The OS moves the process back to the ready state, making it eligible to run again when the scheduler chooses it. Finally, when a process finishes its job or is terminated, it enters the exit state. Often there's a brief intermediate state called zombie right after exit, before the parent process acknowledges its termination and its resources are fully cleaned up.
And the OS provides specific commands, system calls, to trigger these state changes and manage processes. Let's talk about fork. That seems like a really fundamental one for creating new processes.
It is. Fork is a fascinating system call. It creates a new process called the child, which is almost an exact replica of the process they call fork, the parent. They start with identical memory images, the same open file, same environment variables,
Yeah.
everything. The clever trick is how the parent-child know who they are. The fork system call returns a value. In the parent process, it returns the process ID, PID, the newly created child, a positive integer. But in the child process, fork returns 0.
Ah, so the code can just check that return value. If PO0 means I am the child process, and if PDOS means I am the parent, and that's my child's ID.
Exactly. It's a simple but powerful way to differentiate their execution paths right after the fork. Under the hood, the OS allocates a new process structure, assigns a unique PID, allocates a kernel stack for the child, copies the parent's memory map, page directory, copies the parent's saved CPU state, so the child starts executing right after the fork call too, copies file descriptors, the current working directory, and so on. Finally, it sets the child's state to runnable, ready, and returns the appropriate value to both parent and child.
That sounds like a lot of copying, especially the memory map. If the parent process is using gigabytes of RAM, does fork really copy all of that instantly? Seems incredibly inefficient.
That's a key point. Naively copying everything would be very slow and wasteful. So modern operating systems use a crucial optimization called copy on write, or COW. With COW, when fork happens, the OS doesn't actually duplicate the physical memory pages. Instead, it marks the parent's pages as shared between the parent and child, and initially, both just point to the same physical page frames in RAM. The page table entries for both processes initially map to the same physical memory. A real copy of a page is only made if and when either the parent or the child tries to write to that shared page. At that moment, the OS steps in, makes a private copy of that specific page for the writing process, updates its page table, and lets the write proceed on the private copy. The other process continues using the original shared page until it tries to write too.
That's much smarter. So you only pay the cost of copying if you actually modify the data. And often, a child process doesn't modify much before it.
Well, it does something else entirely right. That's where exec comes in. Precisely. The fork exec pattern is extremely common. A process forks to create a child, and then often the child process immediately calls exec. While fork creates a clone, exec, or one of its variants like execv, completely replaces the current process's memory image with a brand new program loaded from an executable file on disk. It doesn't create a new process, it transforms the existing one, the one they called exec.
So like when I type ELS in my shell, the shell forks, the child shell then execs the CLS program, ELS runs and prints the directory listing, and then it exits.
Exactly that sequence. When exec is called, the OS reads the specified executable file, often in ELF format. It validates the file, then throws away the calling process's current memory map, text, data, heap SAC. It sets up a completely new virtual memory space based on the segments defined in the ELF file, loading the new program's code and initialize data from the file into this new space. It creates a fresh user stack, often placing command line arguments and environment variables onto it. Finally, it resets the process's CPU state, crucially setting the instruction pointer, a shape-1 by 86, to the entry point of the new program, usually the start routine, which then calls main. When exec returns, if successful, it technically doesn't return to the caller as the caller's code is gone. The process starts executing the new program from its beginning. Okay, so fork clones, exec transforms. What about the end of the line .exit? Wait. When a process finishes its work, it calls exit. The system call tells the OS it's done. The OS then starts cleaning up. It closes any open files the process had, releases memory, network connections, and other resources. It sets the process state to zombie. This state is important because the process structure still holds some information, like the exit status that the parent process might want. The OS then notifies the parent process if it's waiting. If the exiting process has any children of its own still running, they become orphaned and are typically adopted by a special system process called init, or systemed on modern Linux, which will eventually wait for them. The zombie process itself doesn't run anymore. It just waits to be collected.
And wait, is how the parent collects it, cleans up the zombie?
Yes. The parent process calls wait, or waited. This system call checks if any of the parent's children are in the zombie state. If it finds one, the OS collects the child's exit status, frees the remaining process structure and kernel stack associated with the zombie, and returns the child's PID and status to the parent. The child process is now completely gone. If the parent calls wait, and there are no zombie children, the parent process typically enters the blocked state, until one of its children exits. This synchronization ensures parents can properly manage their children and get their results.
So all these crucial operations, creating, transforming, ending processes, happen through system calls. You mentioned them being the interface to the OS. Why is that interface so necessary? Why can't my program just, I don't know, directly fiddle with the disk controller to write a file?
Security and stability. User programs run in a restricted environment, remember. Lower privilege level, ring 3. The OS kernel runs at a higher privilege, ring 0, and has direct access to hardware and critical system resources. If user programs could directly access hardware or manipulate core OS data structures, a buggy or malicious program could easily crash the entire system, corrupt data, or interfere with other processes. System calls provide a controlled, protected gateway. They are the only legitimate way for a user program to request privileged operations or access shared resources managed by the OS.
It's like having a very strict receptionist, the OS, that you have to go through to get anything important done, rather than wandering into any office you like.
That's a great analogy. You make a request, the receptionist checks if you're allowed, performs the action for you if authorized, and gives you the result.
How does the OS know which service the user program is requesting? There must be hundreds of different system calls. Open, read, write, fork, exit.
It uses a specific mechanism, usually involving a software interrupt or a special trap instruction. Before making the system call, the user program places a unique system call number into a designated CPU register, like EAX on by 86. Then it executes the special instruction, e.g. INT 0 by 80 on older Linux, SYSCAL on modern by 86. This instruction causes the CPU to switch from user mode, ring 3, to kernel mode, ring 0, and jump to a predefined entry point in the OS kernel, the system call dispatcher. The dispatcher code in the kernel then reads the system call number from the saved register, EAX, and uses it as an index into a table of system call handler functions, sysopen, sysread, sysfork, etc. It then invokes the appropriate handler.
And what about arguments? If I call write, I need to pass the file descriptor, the buffer of data, and the number of bytes. How do those get from user space to kernel space?
There are a few common ways for parameter passing. Some systems, like modern Linux on by 8664, pass arguments primarily through CPU registers. The system call number goes in one register, racks the first argument in another, the triad I, the second in another RAI, and so on. This is generally fast. Other systems, like the FE6 example, pass arguments via the user stack. Before executing the trap instruction, the user program pushes the arguments onto its own stack. When the kernel takes over, it knows where the user process's stack pointer was. It's saved as part of the context switch, and can access the arguments directly from the user stack memory.
And the return value, how does that get back?
Similarly, the kernel places the returned value of the system call, e.g. success failure code, number of bytes read, into a specific register, again often EAX or RAX, within the saved CPU state of the user process. When the kernel finishes handling the system call, it executes a special return from interrupt instruction, like IR. This restores the user process's saved CPU state, including the register containing the return value, and switches the CPU back to user mode, resuming the user program right after the trap instruction.
Okay, that system call mechanism makes sense. It's the controlled way in and out of the kernel. Now, this relates directly to CPU sharing and multitasking. We talked about that illusion of doing many things at once. Why bother? Why not just run one program until it's finished?
Because CPUs are incredibly fast, and programs often spend a lot of time waiting. Think about it. When you're typing, the CPU is idle most of the time between keystrokes. When a program reads a large file from a traditional hard drive, the CPU might wait milliseconds, an eternity, in CPU time for the data. If the OS only ran one program at a time, the CPU would sit idle for huge portions of time. Multitasking allows the OS to switch the CPU to another ready-to-run application whenever the current one has to wait. This keeps the CPU busy, dramatically increasing overall system throughput and, crucially for users, responsiveness.
So the OS can just snatch the CPU away from a running process, even if it's in the middle of a calculation.
Yes, that ability is called preemption. The OS can interrupt a running process, take the CPU away, and give it to another process. This is essential for fairness, preventing one CPU-hungry process from hogging the CPU indefinitely, and for responsiveness, ensuring interactive programs get CPU time quickly. The core mechanism that enables this switching is context switching.
Right, context switching. That sounds important and maybe expensive. What exactly happens?
A context switch is a procedure of saving the complete execution state of the currently running process, and then loading the save state of the next process that the scheduler has chosen to run. This state or context includes everything needed to resume the process later exactly where it left off. general purpose, instruction pointer, stack pointer, status flags. The process's memory management information, like the pointer to its page table, open file status, etc.
What triggers a context switch?
There are generally three main triggers. 1. Blocking on I/O. The currently running process makes a system call that requires waiting. For example, reading from disk, waiting for network input. It voluntarily gives up the CPU. 2. Process termination. The process finishes execution and calls exit. 3. Timer interrupt. This is the key to preemption. A hardware timer chip interrupts the CPU at regular intervals, for example, every 10 or 100 milliseconds. The OS's timer interrupt handler runs, realizes the current process has used up its allotted time slice or quantum, and invokes the scheduler to pick a new process. This forces a context switch, even if the current process didn't voluntarily yield.
Okay, saving and loading all that state, that can't be free. What are the overheads involved?
You're right, context switching isn't free. There are significant overheads which can be broken down into direct and indirect costs. The direct costs are the obvious ones. The time it takes the CPU to respond to the interrupt, the time spent executing the OS code to literally save the old process's registers and load the new ones, and the time the scheduler itself takes to decide which process runs next.
But you mentioned indirect costs. Those sound more subtle.
They often have a bigger performance impact. When you switch to a new process, the CPU's caches are suddenly full of data and instructions from the old process. One key example is the TLB, Translation Look-Aside Buffer. This is a hardware cache that stores recent virtual to physical address translations from the page table to speed up memory access. When you switch processes, the TLB entries for the old process are useless for the new one, so the TLB often needs to be flushed and validated. The new process then suffers TLB misses as it runs, having to go back to the main page table in memory, which is slower, until the TLB warms up with its own translations. Similarly, the CPU's data and instruction caches lose their effectiveness. The new process likely needs different data and code than the old one, leading to cache misses and forcing fetches from slower main memory. The CPU's instruction pipeline might also need to be flushed and refilled. All these indirect effects disrupt the smooth flow of execution and can significantly degrade performance if context switches happen too frequently.
So there's a real balancing act. You need context switches for multitasking and responsiveness, but too many hurt performance. This makes CPU scheduling the art of deciding who runs when and for how long absolutely critical. How does the US make those decisions?
The first step is often understanding the type of process. Schedulers typically differentiate between CPU-bound and I/O-bound processes. A CPU-bound process is one that performs long computations and doesn't do much I/O. Think compiling a massive project like GCC or running complex simulations. These processes have long CPU bursts. They can often tolerate slightly lower priority or less frequent scheduling as long as they make progress. An I/O-bound process, on the other hand, does very little computation between I/O operations. Think of a word processor waiting for your key presses, or a web server waiting for network requests. They have very short CPU bursts followed by long waits for I/O. These processes need higher priority and quick access to the CPU when they are ready to ensure the system feels responsive. You don't want lag when typing.
That makes sense. Prioritize the interactive stuff. What are some of the classic scheduling algorithms used to manage these different types?
Let's look at a few foundational ones conceptually. First come, first served. FCFS. The simplest. Processes join a queue, and the CPU is allocated to the process at the head of the queue when it becomes free. It runs until it blocks or finishes. It's non-preemptive. The big problem, the convoy effect. If a very long CPU-bound process gets the CPU, lots of short I/O-bound processes might get stuck waiting behind it, leading to poor average response time.
Yeah, sounds like waiting in line behind someone with a cart full of complicated coupons.
Exactly. Shortest job first, SJF. This one is theoretically optimal. It minimizes the average waiting time. The idea is to always pick the process with the shortest next CPU burst, the catch. It's impractical because you can't accurately predict the future how long the next CPU burst will be. There's a preemptive version called shortest remaining time first, SRTF, where if a new process arrives with a shorter remaining burst time than the currently running process, it preempts it. Still relies on prediction, though.
Okay, so FCFS is simple but unfair. SJF is optimal but impossible. What's actually used?
Round robin, R. This is a very common, practical, preemptive algorithm designed for fairness and time sharing. Each process in the ready queue gets a small unit of CPU time, called a time slice or quantum. This quantum is typically somewhere between 10 and 100 milliseconds in modern systems. The Pi v6 example used 10 meters. When a process's time slice expires, the timer interrupt goes off, the OS preempts the process, even if it's not finished, moves it to the back of the ready queue, and dispatches the process at the front of the queue for its own time slice.
The length of that time slice must be critical then, right? What's the trade-off?
Absolutely critical. It's a fundamental trade-off. A short time slice, for G 10 meters, means processes get swapped frequently. This gives excellent response time for interactive tasks. You feel like the system is reacting quickly. But it means lots of context switches, and as we discussed, context switches have high overhead, potentially lowering overall system throughput. A long time slice, CB 500 meters, reduces the context switching overhead. But the scheduler starts behaving more like FCFS. Response time suffers because interactive processes might have to wait a long time for their turn, making the system feel sluggish. Finding the right quantum length is a key tuning parameter for OS designers.
What about adding priorities into the mix? Priority-based scheduling.
Yes, that's another common approach, often combined with others. Each process is assigned a priority number, and the scheduler always chooses the highest priority-ready process to run. This is crucial for systems with real-time requirements. Think anti-lock brakes in a car, where the braking process must have the highest priority. The big danger with simple priority scheduling is starvation. Low-priority processes might never get to run if there's a constant supply of higher priority tasks.
How do they fix starvation? Just let the low-priority tasks starve?
No, that's generally unacceptable. A common technique to prevent starvation is aging. The OS gradually increases the priority processes that have been waiting in the ready queue for a long time. Eventually, even a low-priority task's priority will rise high enough for it to get scheduled. Once it runs, its priority might be reset to its original base level.
I've also seen multi-level feedback queues mentioned. That sounds complex. How did that work?
They are a bit more sophisticated, yes. The idea is to have multiple ready queues, each representing a different priority level. Processes can move between these queues based on their behavior. For example, a process might start in a high-priority queue. If it uses its entire time slice, indicating it's likely CPU-bound, it might get demoted to a lower priority queue with a longer time slice. If a process in a lower priority queue blocks for I/O before its time slice ends, indicating it's likely I/O-bound, it might get promoted back to a higher priority queue with a shorter time slice to improve its responsiveness.
It's a way for the scheduler to dynamically adapt to the changing behavior of processes.
That's clever, sort of learning about the process as it runs. Now, all this gets even more complicated when you have multiple CPUs or cores, right? Multi-processor scheduling. It definitely adds another layer of complexity. How do you decide which process runs on which core? Historically, some systems used asymmetric multiprocessing, AMP. One CPU, the master, handled all scheduling decisions and kernel tasks, while the other CPUs, the slaves, only executed user code. This is simple, but the master CPU quickly becomes a bottleneck.
So modern systems use symmetric multiprocessing, SMP.
Exactly. In SMP, all CPUs are peers. Each CPU can run the scheduler and execute kernel code independently. The main question then becomes, how do they manage the ready queue? There are two main approaches. Global queue. All CPUs share a single, common ready queue. When a CPU becomes idle, it grabs the next process from this shared queue. This provides good load balancing and fairness naturally, but the big downside is lock contention. Multiple CPUs trying to access and modify the same shared queue requires locking, which introduces overhead and can become a bottleneck itself, especially with many cores. Per CPU queues. Each CPU has its own private ready queue. When a CPU needs a new task, it just looks at its own queue. This is much faster and avoids lock contention. The challenge here is potential load imbalance. One CPU might have a long queue of waiting tasks while another CPU sits idle.
So if you use per CPU queues, you need some way to fix that imbalance.
Yes, you need load balancing mechanisms. These try to periodically redistribute tasks to keep the load even across all CPUs. Two common techniques are push migration, where an overloaded CPU actively pushes some of its tasks on the less busy CPUs, and pull migration, where an idle or less busy CPU actively pulls tasks from overloaded CPUs. But there's a catch. Moving a process from one CPU's queue to another, process migration, is expensive. The process might lose cache affinity, its data was warm in the old CPU's cache, and TLB entries need reestablishing. So load balancing algorithms try to migrate processes only when the imbalance is significant enough to justify the cost.
Okay, let's ground this in a real-world example. How does scheduling in Linux work? Has it changed over time?
Linux scheduling has evolved significantly. It classifies processes into real-time and normal. Real-time processes have strict priorities and scheduling policies like FIFO or RRR, designed for applications with hard deadlines. Normal processes are the standard user applications. Linux further tries to heuristically classify these as interactive, I/O-bound, needs good responsiveness, or batch, CPU-bound, can run in the background. This classification influences scheduling decisions. Over the years, Linux has used different schedulers, like the older ON scheduler than the O1 scheduler, which aimed for constant time scheduling decisions regardless of the number of tasks.
But the current default, the one that's been dominant for a while, is the completely fair scheduler, CFS, right?
That's right. CFS became the default normal process scheduler in Linux 2.6.23 back in 2007, and it's based on a really interesting idea. Its goal, as the name implies, is to be completely fair in distributing processor time. Instead of fixed time slices, CFS uses a concept called virtual runtime. Each task accumulates runtime as it executes. The scheduler always tries to run the task with the lowest runtime, the task that has had the least amount of CPU time relative to its fairness share.
So it's constantly trying to balance out the execution time each task has received.
Exactly. To efficiently find the task with the minimum runtime, CFS uses a red-black tree, a type of self-balancing binary search tree, to store the runnable tasks, ordered by their runtime. Picking the next task to run is simply a matter of picking the leftmost node in the tree, which is very fast. What's really elegant is how CFS naturally handles I/O-bound versus CPU-bound processes without explicit classification. An I/O-bound task spends a lot of time sleeping, blocked. When it wakes up, its runtime hasn't increased much compared to CPU-bound tasks that kept running. So it naturally appears more deserving of the CPU, has a lower runtime, and gets scheduled quickly. It also tends to get dynamically larger affected time slices when it does run, promoting responsiveness.
That's a really neat self-regulating approach. Okay, so we focused on processes as these fairly heavyweight, isolated things. But for parallelism within an application, creating a whole new process seems like overkill sometimes. This brings us to threads. Lightweight parallelism.
Precisely. Using full-blown processes for parallel tasks within a single application has downsides. As we discussed, fork can be expensive due to memory map duplication, even with CLW. And because processes are isolated, getting them to communicate and share results requires inter-process communication, IPC mechanisms, which often involve system calls and data copying, adding complexity and overhead.
So threads are the answer for finer-grained parallelism.
Yes, threads are often called lightweight processes. They represent a basic unit of CPU utilization within a single process. The key difference and advantage is that multiple threads belonging to the same process share resources. They share the same code segment, text, the same global variables, data segment, the same dynamically allocated memory, and the same open files and other OS resources.
But they must have something private, otherwise how could they run independently?
They do. Each thread has its own private stack and its own set of CPU registers, including the program counter and stack pointer. The stack holds local variables and function call information specific to that thread's execution path. The registers hold its current execution state. This allows multiple threads to execute different parts of the same program concurrently, or the same part on different data.
And the benefits are significant.
Huge benefits for certain kinds of parallelism. Lower overhead for creation, termination, and context switching compared to processes. Switching threads within the same process doesn't necessarily require changing the memory map, which saves TLB flushes. And crucially, efficient communication, since threads share memory, they can communicate simply by reading and writing shared variables. No complex IPC needed, though you still need synchronization, which we'll get to.
You mentioned thread earlier.
Right.
How might that look in practice? Say, summing a huge array of numbers.
Right. Using a library like Threads, P06 Threads, a standard API for thread management, you typically divide the large array into, say, 4 chunks. The main thread would then use thread create 4 times, creating 4 new worker threads. Each thread create call would specify a function for the new thread to run, e.g. some chunk, and pass it the information about which chunk of the array it's responsible for. Each worker thread calculates its partial sum. The main thread then uses thread join to wait for each of the 4 worker threads to finish. Once they're all done, thread join returns the results, the partial sums, and the main thread adds them up to get the final total. This can be much faster on a multi-core machine than doing the whole sum sequentially.
Sounds powerful. But I recall reading about different types of threads, user level versus kernel level. What's the distinction there?
This is about who manages the threads, the application itself, or the operating system kernel. User-level threads. These are implemented entirely by a thread library running in user space, like an older Green Threads implementation. The kernel is completely unaware of these threads. It just sees the single main process. Pros: very fast creation and switching. Since it's all done in user space, there are no system calls, no kernel mode switches needed. Cons: big one. If one user-level thread makes a blocking system call, like reading from a file, the entire process blocks because the kernel doesn't know other threads might be ready to run. Also, they can't take advantage of multiple CPU cores, as the kernel only schedules the single process they belong to. Kernel-level threads. These are supported and managed directly by the operating system kernel. Each thread is treated by the kernel as a separate schedulable entity. Modern OSs like Linux, Windows, macOS predominantly use kernel-level threads, often with a mapping model like 1.1, one user thread maps to one kernel thread. Pros: if one thread blocks on a system call, the kernel can schedule another thread from the same process or a different process to run. They can run a true parallel on multi-core systems because the kernel can schedule different threads onto different cores. Cons: they have higher overhead. Creating, managing, and switching kernel threads involves system calls and kernel intervention, which is slower than user-level operations. The kernel also needs to maintain more state information for each thread.
So it sounds like kernel-level threads are generally the way to go for real concurrency on modern hardware, despite the overhead. But threading must introduce some weird edge cases, right? Like, what happens if a thread calls fork? Or if one thread gets a segmentation fault?
Absolutely. These are complex issues OS designers had to resolve. When a thread calls fork, does the new child process duplicate all the threads of the parent, or just the single thread that called fork? Different systems have made different choices. Similarly, if one thread causes a fatal error like a segmentation fault, should the OS terminate just that one faulty thread, or is the entire process considered compromised, since they share memory, and thus the whole process should be terminated? Again, policies vary, but often the entire process is terminated because shared state might be corrupted. These decisions have big implications for programmers writing multi-threaded applications.
Okay, processes are isolated, threads share memory, but they often need to cooperate or coordinate. This brings us to interprocess communication, IPC for processes, and the whole challenge of managing shared access, which is synchronization. How do those isolated processes talk?
Since processes live in their own sandboxes, they need explicit OS-provided mechanisms for IPC. One very common and high-performance method is shared memory. The idea is one process asks the OS to create a special region of physical RAM that is designated as shared. Then other authorized processes can ask the OS to attach this same shared memory segment into their own virtual address space.
So multiple processes can have a chunk of memory that's actually the same physical RAM mapped into their different virtual address spaces.
Exactly. Once attached, processes can read and write to this shared memory region just like it was their own private memory, using standard load and store instructions. This makes communication extremely fast because after the initial setup, using system calls like schmigit and schmat in Unix-like systems, data transfer doesn't involve the kernel at all. The big challenge with shared memory, though, is that the processes themselves are entirely responsible for synchronizing their access to avoid corrupting the shared data. The OS just provides the shared space. It doesn't manage the access conflicts.
Okay, speed versus complexity. What's another way? Message passing. Like pipes?
Yes, message passing is another major IPC paradigm. Instead of sharing memory directly, processes communicate by sending and receiving discrete messages. The OS typically manages the message queues or channels. Pipes are a classic form of message passing in Unix-like systems. A pipe provides a unidirectional channel. Data written by one process to the right end of the pipe is buffered by the kernel and can then be read by another process from the read end. It's like a simple conveyor belt for bytes.
So maybe a parent process creates a pipe, then forks a child. The child could write its results into the pipe and the parent could read them out.
That's a very common use case, yes. There are also other message passing mechanisms like message queues, sockets for network communication, which can also be used locally, etc.
And what about signals? They seem simpler.
Signals are more like asynchronous notifications or alerts sent to a process. They signal events like terminate yourself, sigterm, you accessed bad memory, 6ect, or user-defined events. They're a fairly basic form of IPC, not really suitable for transferring large amounts of data.
Okay, whether it's shared memory between processes or threads implicitly sharing memory, this concurrent access leads to major challenges. You mentioned race conditions. Let's unpack that. What exactly is the problem?
The core problem arises when multiple processes or threads access and modify the same shared data concurrently. Because the execution of their instructions can be interleaved in unpredictable ways due to scheduling interrupts, the final value of the shared data depends on the precise timing and order of operations. This is a race condition. The result races to depend on who gets there first or in what order.
Can you give us a simple, concrete example, like incrementing a counter?
Perfect example. Let's say we have a shared integer variable counter, initially 5. Process A wants to execute counter plus 1, and process B wants to execute counter 1. Ideally, after both run, the counter should be back to 5. But look at the low-level machine instructions. Incrementing might involve 1. Load counter, value 5, from memory into a CPU register. 2. Increment the value in the register. Register now holds 6. 3. Store the register value 6 back into memory location counter. Decrementing is similar. Load 5, decrement register to 4, store 4.
Okay, 3 steps each.
Now imagine this interleaving. 1. Process A loads counter 5 into its register. 2. Process A increments its register, now holds 6. 3. Context switch. Process B gets the CPU. 4. Process B loads counter, still 5, A hasn't stored yet, into its register. 5. Process B decrements its register, now holds 4. 6. Process B stores its register value, 4. Back into counter. Memory counter is now 4. 7. Context switch. Process A gets the CPU back, 8. Process A resumes and stores its register value, which is still 6, back into counter. Memory counter is now 6. We started at 5, did an increment and a decrement, and ended up at 6. If the interleaving happened differently, we could have ended up at 4. The result is wrong and unpredictable. That's the race condition.
Yikes. That's subtle but clearly disastrous for correctness. So the section of code where this shared data is accessed, like the counter plus 1 line, is called the critical section. The goal is to make sure only one process or thread can be inside its critical section for that shared data at any given moment.
Exactly. We need mutual exclusion for critical sections accessing the same shared resource.
What are the essential properties that any solution to this critical section problem must have?
There are generally 3 accepted requirements for a correct solution. 1. Mutual exclusion. As we said, if one process is executing in its critical section, no other processes can be executing in their critical sections for the same shared resource. 2. Progress. If no process is in its critical section and some processes want to enter, then the selection of the next process to enter cannot be postponed indefinitely. Also, only processes that are not currently executing outside their critical section in their remainder section can participate in this decision. Basically, you can't have a situation where everyone wants in, but nobody can get chosen. 3. Bounded waiting. There must be a limit on the number of times other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. This prevents starvation. A process shouldn't have to wait forever to get its turn.
Mutual exclusion, progress, bounded waiting. Got it. So how do we actually achieve this? What are the synchronization primitives operating systems and programmers use?
Well, let's start with a simple but limited idea. Disabling interrupts. On a single-core CPU, if a process disables all interrupts before entering its critical section and re-enables them immediately after exiting, it guarantees atomicity. Why? Because interrupts are how context switches due to timers or I/O completions happen. No interrupts, no context switches, no interleaving.
But that sounds dangerous. And what about multi-core systems?
It is dangerous if used carelessly. What if interrupts are never re-enabled?
Oh.
And you're right, it's completely ineffective on multi-core systems. Disabling interrupts on Core 1 doesn't stop Core 2 from running concurrently and accessing the same shared data. So this isn't a general solution for modern hardware.
Okay, so disabling interrupts is out. What about pure software solutions, trying to coordinate just using shared variables?
People tried this for years. There were many early attempts that looked promising, but were later found to be flawed. They might violate mutual exclusion under certain interleavings, or they might violate progress, leading to deadlock, or bounded waiting, leading to starvation. A famous correct software solution for 2 processes is Peterson's solution. It cleverly uses shared flag variables, indicating intent to enter, and a shared turn variable to break ties if both intend to enter simultaneously. It provably guarantees all 3 properties. For N processes, Leslie Lamport developed the bakery algorithm. It's conceptually elegant. Processes take a ticket number before entering. The process with the lowest number gets to enter the critical section, like at a real bakery. Ties are broken using process IDs. Implementing the ticket-taking atomically and fairly without hardware support is the tricky part, often involving a shared choosing array. While theoretically important, these pure software solutions tend to be complex and less efficient than hardware-assisted methods.
Right. So that brings us to hardware locks, using special processor instructions.
Exactly. Modern CPUs provide atomic hardware instructions specifically designed for building synchronization primitives much more efficiently. A classic example is the test and set instruction. Test_set target atomically reads the current Boolean value at memory location target, sets the value at target to true, and returns the original value it read. The key is atomicity. The read and the write happen as one indivisible operation. Even if multiple cores execute test_set on the same location simultaneously, the hardware guarantees they happen sequentially, not interleaved.
How does that help build a lock?
You can use it to implement a simple lock, often called a spin lock. You have a shared Boolean variable, say lock held, initialized to false. To acquire the lock, a process repeatedly executes while test_set true. If test_set returns false, it means the lock was free, and the process just atomically set it to true. So now holds the lock and can exit the loop and enter the critical section. If test_set returns true, it means the lock was already held and test_set left it as true, so the process just loops and tries again.
So it just sits there, spinning in a tight loop, burning CPU cycles, constantly checking the lock.
Precisely. That's why it's called a spin lock. Pros: very low overhead if the critical section is extremely short in contention. Multiple processes trying to get the lock at once is low. There's no expensive context switch involved in waiting. Cons: terrible CPU wastage if the lock is held for a long time, or if the waiting process has to wait for something like disk I/O. The spinning CPU isn't doing any useful work. Also, on multi-core systems, careful implementation is needed to handle cache coherency, ensuring the test_set or similar instruction forces communication with main memory or other caches. The XPG instruction on by86 and other atomic swap is often used for spin locks and typically needs a lock prefix to ensure atomicity across cores and handle caches correctly.
Okay, spin locks are good for tiny critical sections, bad for long waits. That seems like a job for mutexes. They let the process sleep instead of spin, right? Exactly. Mutexes, mutual exclusion objects, are designed to overcome the CPU wastage of spin locks for longer waits. A mutex is essentially a lock with an associated waiting queue. When a process tries to acquire a mutex, lock mutex, that is already held by another process, instead of spinning, the OS puts the requesting process into the block state and adds it to a queue of processes waiting specifically for this mutex. The OS then performs a context switch to run some other ready process. When the process currently holding the mutex finishes its critical section and calls unlock mutex, the OS checks the mutex's waiting queue. If there are processes waiting, it picks one, for AG, the one waiting longest, moves it from the block state back to the ready state, making it eligible to run and eventually acquire the mutex. That definitely saves CPU cycles compared to spinning. Are there any downsides to mutexes?
Yes, they introduce their own complexities. Context switching itself has overhead. Also, a naive implementation where unlock wakes up all waiting processes can lead to the thundering herd problem. Dozens of processes wake up, all try to acquire the lock at once, most fail, and immediately go back to sleep, causing a storm of context switches and contention. Modern mutex implementations are smarter and typically wake only one specific waiting process. Another more serious issue that can arise with mutexes and priority-based scheduling is priority inversion.
You mentioned this briefly. Explain that again. It sounds bad.
It can be catastrophic, especially in real-time systems. Imagine you have a high-priority task, H, and a low-priority task.
Right.
Task L acquires a mutex needed by task H. Now, task H becomes ready to run, preempts L because H has higher priority, and tries to acquire the mutex. But it can't because L holds it. So H locks, waiting for L. Now, here's the inversion. A medium priority task, M, becomes ready. Since M has higher priority than L, which is currently holding the resource H needs, M preempts L. So L doesn't run, meaning it can't finish its critical section and release the mutex. As a result, the high-priority task H is effectively blocked not just by the low-priority task L, but also by any medium-priority tasks that happen to run. H's execution is delayed indefinitely by lower-priority activity. This famously caused problems for the Mars Pathfinder mission.
Wow. Okay, so mutexes solve spinning but introduce potential blocking issues like priority inversion. What about semaphores? Are they just fancier mutexes?
Semaphores are a more generalized synchronization tool invented by Edsger Dijkstra. A semaphore is essentially an integer variable that supports two atomic operations, down, also called wait or P, decrements the semaphore value. If the value becomes negative, the process calling down is blocked and placed on the semaphore's waiting queue, up, also called signal or V, increments the semaphore value. If the value is negative, meaning processes are waiting, it wakes up one of the blocked processes, moving it to the ready queue. A mutex can be thought of as a special type of semaphore called a binary semaphore, initialized to one lock is like down, unlock is like up. But semaphores can also be initialized to other values, making them useful as counting semaphores. For example, a semaphore initialized to n could be used to control access to n identical resources, like database connections in a pool, Down acquires a resource, up releases it.
Can you give another classic example where semaphores shine?
The producer-consumer problem is the canonical example. You have one or more producer processes threads adding items to a shared buffer, and one or more consumer processes threads removing items from it. You need to ensure producers don't add to a full buffer and consumers don't remove from an empty buffer, and also that access to the buffer itself is mutually exclusive. This is typically solved using 3 semaphores. 1. Empty. A counting semaphore initialized to the buffer size n, producers down empty before adding an item, waits if buffer is full. 2. Full. A counting semaphore initialized to 0, consumers down full wall before removing an item, waits if buffer is empty. 3. Mutex. A binary semaphore, or mutex, initialized to 1. Both producers and consumers must down mutex before accessing the buffer structure itself and up mutex afterwards, ensuring only one touches the buffer at a time. Producers up full after adding an item, consumers up empty after removing one. It elegantly coordinates everything.
And the dying philosopher's problem. That also uses semaphores.
Yes, that's another classic concurrency puzzle used to illustrate the difficulty of avoiding deadlock while allocating resources. You have 5 philosophers sitting around a table needing 2 forks, one to their left, one to their right, to eat. There are only 5 forks total placed between them. If every philosopher simultaneously picks up their left fork, they all become blocked, waiting for the right fork, which is held by their neighbor. Nobody can eat, nobody can release a fork, a perfect deadlock. Semaphores, for example, one for each fork, or a more sophisticated solution limiting the number of philosophers trying to eat at once, can be used to design a deadlock-free solution.
That's a perfect segue. We've seen how synchronization is needed, but when it goes wrong, or when resource allocation gets tangled, we hit deadlocks. What's the formal definition again?
A deadlock is a state where a set of 2 or more processes are blocked indefinitely, each holding some resources and waiting to acquire resources held by another process within the same set. It's a circular wait dependency for resources.
And you mentioned earlier there are 4 necessary conditions for a deadlock to even be possible. What are they again? All 4 must hold.
Yes, all 4 must be present simultaneously for a deadlock to potentially occur, though their presence doesn't guarantee one will occur. 1. Mutual exclusion. At least one resource involved must be held in a non-shareable mode. Only one process can use it at a time, e.g. a printer, a lock on a file. If resources were shareable, deadlock wouldn't happen over them. 2. Hold and wait. A process must be holding at least one resource while waiting to acquire additional resources currently held by other processes. 3. No preemption. Resources cannot be forcibly taken away, preempted, from a process holding them. A process must release resources voluntarily. 4. Circular wait. There must exist a cycle of processes P0, P1, 3ON, such that P0 is waiting for a resource held by P1, P1 is waiting for a resource held by P2, and Pn is waiting for a resource held by P0.
So if you could just break one of those conditions, you could prevent deadlocks entirely.
Theoretically, yes. But practically, breaking each condition often comes with significant downsides, or might be impossible for certain resource types.
It's also interesting that deadlocks are probabilistic. Just because the conditions exist doesn't mean it will happen.
Right. The exact timing of resource requests and releases matters immensely. A slightly different order of execution might completely avoid a potential deadlock situation. They are often rare events, which complicates deciding how much effort to put into handling them.
So how do real systems deal with deadlocks? Ignoring them sounds appealing but risky.
There's a spectrum of approaches. 1. The ostrich algorithm. Seriously, just ignore the problem. This is surprisingly common in many general-purpose operating systems like Linux and Windows. The rationale is that deadlocks are sufficiently rare, and the performance overhead and complexity of prevention or detection mechanisms outweigh the benefit for most users. If a deadlock happens, the user might just have to reboot or manually kill processes. 2. Detection and recovery. This involves letting deadlocks happen, but having the OS periodically run a deadlock detection algorithm, ADMARY, by analyzing a resource allocation graph looking for cycles. If a deadlock is detected, the OS needs to recover. Recovery usually involves either process termination, aborting one or more processes in the deadlock cycle. Which one is to choose is a tricky policy decision. Here's the lowest priority. Most recently started, fewest resources held. Resource preemption. Forcibly taking resources away from some processes in the cycle and giving them to others until the cycle is broken. This also requires rolling back the preempted process to a safe state, which can be very complex, needs checkpointing. 3. Deadlock avoidance. This approach requires the OS to have some advanced knowledge about the resources a process might request in the future. Before granting any resource request, the OS checks if granting it would leave the system in a safe state, meaning there exists some sequence of future resource allocations that allows all processes to eventually finish without deadlocking. If granting the request would lead to an unsafe state, which might lead to deadlock, the request is denied and the process waits. The banker's algorithm is the classic example of an avoidance algorithm, treating resources like units of credit. It's powerful, but requires knowing maximum resource needs up front, which isn't always practical. 4. Deadlock prevention. This is the most proactive strategy. You design the system so that at least one of the 4 necessary conditions can never hold. Prevent mutual exclusion. Make resources shareable, often impossible, for example, physical printer. Prevent hold and wait. Require processes to request all needed resources at the beginning or release all held resources before requesting new ones. Can lead to low resource utilization or potential starvation. Prevent no preemption. Allow the OS to forcibly take resources away. Difficult for some resource types, like a printer mid-job. And needs rollback mechanisms. Prevent circular wait. Impose a total ordering on all resource types. Require processes to request resources only in increasing order of this assigned number. This is often a practical prevention technique, e.g. always lock mutex A before mutex B.
Wow, quite a range of strategies, from burying your head in the sand to very complex avoidance and prevention schemes. It really highlights how tricky managing concurrent resource access is. Okay, we've seen how the OS manages processes, schedules them, helps them synchronize, and tries to prevent deadlocks. Now let's shift focus to the explicit role of the OS in fortifying the system. Operating system security. What are the high-level goals here?
OS security fundamentally aims to achieve 3 core properties, often called the CIA triad, though slightly adapted for OS context. 1. Availability, ensuring that system resources, CPU, memory, files, network access, are available to authorized users when needed. This involves preventing things like denial of service attacks, where one process unfairly hogs resources. 2. Confidentiality, protecting data and system information from unauthorized disclosure, ensuring only users or processes with the correct permissions can read sensitive information. 3. Integrity, preventing unauthorized modification or destruction of data and ensuring system resources operate correctly, ensuring data is trustworthy and hasn't been tampered with.
Availability, confidentiality, integrity. And the main tool the OS uses to enforce these is access control, right? Deciding who gets to do what to what.
Exactly. Access control is the heart of OS security. It's the mechanism that mediates every attempt by a subject, like a user, or a process acting on behalf of a user, to perform an operation, like read, write, execute, create, delete, on an object, like a file, a directory, a memory segment, a device. The access control system needs to evaluate every access request against a defined policy and permit only authorized accesses.
What are the key components needed to build a solid access control system?
You generally need 3 layers. 1. Security policy. This defines the high-level security goals and rules, what needs protection, from whom, what constitutes a threat. Ideally, it should be succinct, precise, and complete. Often, policies start vague, protect user files, and need refinement. 2. Security model. This is a more formal, often mathematical representation of the security policy. It provides a precise way to specify rules and helps in analyzing the policy for gaps or inconsistencies. Models like Bella Padula or BIBA fall into this category. A good model can help prove certain security properties. 3. Security mechanism. This is the actual implementation, the code and data structures within the OS that enforce the policy based on the model. For a mechanism to be effective, it needs several properties. It should be correct, bug-free, tamper-proof, users can't disable it, non-bypassable, all accesses must go through it, and ideally implemented within a small, verifiable part of the OS, often called the security kernel or reference monitor.
Let's talk about the most common type most users encounter. Discretionary access control, DAC. This is like standard file permissions, isn't it? Based on user identity.
It is. DDAC controls access based on the identity of the subject, user group, and potentially on groups they belong to. The key characteristic of discretionary is that the owner of an object, example, the user who created a file, typically has the discretion to grant or revoke permissions for that object to other users.
So I create a file. I can decide if my colleagues can read it or write to it.
Exactly. The classic conceptual model for DC is the access matrix. Imagine a giant grid where rows are subjects, users' processes, and columns are objects, files, devices. The cell at row column contains the specific rights, read, write, execute, own, that the subject has for that object. Of course, a literal matrix would be huge and mostly empty, sparse, so real systems use more practical implementations. Authorization tables. A list of tuples, like user-write-object, needs searching,
Okay.
capabilities, C-lists. Each subject holds a list of unforgeable tokens, capabilities, where each token specifies an object and the rights the subject has for it, like having a set of keys. Good for distributed systems, but managing revocation and preventing capability theft can be tricky. Access control lists, ACLs. Each object has a list attached to it specifying which subjects have which rights. Subject rights. This is very common. Standard Unix file permissions, the 9 bits for owner, group, others for read, write, execute, are a simplified form of ACL. More extensive ACLs allow finer-grained control.
DAC seems straightforward, but it has well-known weaknesses. The big one is the Trojan horse attack, right?
Yes, that's a fundamental flaw in DICE reliance purely on identity. A Trojan horse is malicious code hidden inside a seemingly legitimate program. When an authorized user runs this program, the Trojan code executes with all the privileges of that user and the program itself. If you, as an administrator, root superuser, accidentally run a program containing a Trojan, that Trojan can do anything the administrator can do: delete files, install malware, change passwords. The doesn't-make mechanism can't distinguish between legitimate actions requested by the admin via the program and malicious actions initiated by the hidden Trojan code within that same program, because they both originate from a process running with the admin's identity.
And DAC also doesn't control where information flows after access is granted.
Right. That's the other major limitation. DOC controls access, but not information flow. If user Alice has permission to read a sensitive file, secret.doc, DICE doesn't prevent Alice from making a copy of it called public.doc and granting read permission to everyone. The sensitive information is flowed from a protected context to an unprotected one, entirely within the rules of DICE.
So to address these issues, especially information flow and Trojans, we have mandatory access control, AMIC. How does that differ?
MEC takes a fundamentally different approach. Instead of relying on user discretion, it enforces system-wide information flow policies based on security labels, or classifications, assigned to both subjects, users' processes, and objects, files data. These policies are mandatory. Users cannot override them. The most famous MEC model focused on confidentiality is the Bella-Padula model, BLP.
What's the core idea of Bella-Padula, keeping secrets secret?
Exactly. BLP aims to prevent information from flowing from a high security level, for example, top secret, to a lower security level, for example, unclassified. It enforces this using 2 main rules. 1, simple security property, no read-up. A subject can only read information from objects at its own security level or below. A user cleared for secret cannot read a top secret document. 2, property, no write-down, pronounced star property. A subject can only write information to objects at its own security level or above. A process running at secret level cannot write data into an unclassified file. This rule directly counters the Trojan horse leak problem. Even if a Trojan runs at secret level, it's prevented from leaking that secret data into a lower-level public file.
Okay, no read-up, no write-down for confidentiality, but you mentioned it doesn't handle integrity.
Sure.
What if a low-security user writes garbage into a high-security file? The LP allows that.
Correct. BLP's no write-down allows writing up, which can compromise integrity. To address this, the BIBA model was developed, focusing purely on integrity.
And BIBA is basically the inverse of BLP's rules.
Pretty much. BIBA assigns integrity levels, DG, high, medium, low, and aims to prevent low-integrity data from corrupting high-integrity data. Its rules are: 1, simple integrity property, no read-down. A subject can only read objects at its own integrity level or above. A high-integrity process shouldn't be contaminated by reading low-integrity untrusted data. 2, integrity property, no write-up. A subject can only write to objects at its own integrity level or below. A low-integrity process cannot modify high-integrity data. Together, BLP and BIBA provide strong theoretical foundations for controlling both confidentiality and integrity, though implementing them fully in practical systems can be complex.
These models sound powerful, yet we still hear about vulnerabilities all the time. Let's dive into a really common, persistent one: buffer overflows. Even with these access control models, bugs happen, right?
Absolutely. Modern OS kernels are massive, millions of lines of code. It's practically impossible for them to be bug-free. Attackers are constantly searching for and exploiting these bugs, especially memory corruption vulnerabilities, to bypass security mechanisms and gain unauthorized access or control. The stack buffer overflow is a classic and still relevant example.
Okay, walk us through how a stack buffer overflow attack actually works. Remind us about the stack layout first.
Right. Remember the call stack. When a function is called, a new stack frame is pushed onto the stack. This frame typically contains the parameters passed to the function, the return address, the memory address in the calling function where execution should resume after this function finishes, possibly a saved frame pointer, pointing to the previous stack frame, and finally space for the function's local variables, including arrays or buffers. On most architectures, the stack grows downwards in memory.
So local buffer, then save frame pointer, then return address, then parameters, all stacked up. And the attack involves writing past the end of that local buffer.
Exactly. The overflow happens when a program tries to copy data into a local buffer, but the input data is larger than the buffer's allocated size. Because C doesn't automatically check boundaries on basic array writes, example, using stripy or bat7, the excess data gets written past the end of the buffer, overriding whatever comes next on the stack.
And next, it often means the return address.
Critically, yes. If the attacker provides enough oversized input, they can overwrite the saved return address on the stack. Now for the exploitation. The attacker doesn't just overwrite the return address with junk. They carefully craft the input data so that, 1, it includes malicious machine code called shellcode, typically designed to start a command shell, binsh, giving the attacker interactive control. 2, this shellcode is placed somewhere controllable within the overflowing input data, often within the buffer itself. 3, the part of the input that overwrites the return address contains the exact memory address where the attacker placed their shellcode on the stack. When the vulnerable function finishes and executes its return instruction, instead of jumping back to the legitimate caller, the CPU reads the attacker-controlled return address from the stack and jumps directly to the attacker's shellcode, executing it with the privileges of the compromised program. Game over.
That's chillingly precise. But wait, modern systems have defenses like the NX bit, non-executable stack. Doesn't that stop attackers from executing shellcode placed on the stack?
It's a very important defense, yes. The NX bit, or Data Execution Prevention DEP, allows the OS to mark memory pages, including the stack, as non-executable. If the CPU tries to jump to and execute code on an NX-protected page, it causes a hardware exception and the program usually crashes, thwarting the direct shellcode injection attack. But attackers are clever. They develop bypass techniques. One major one is the return alybic attack.
How does that work around NX?
Instead of trying to execute shellcode on the stack, the attacker overwrites the return address with the address of an existing legitimate function that's already loaded in memory as part of a shared library, like the standard C library, libshic. A common target is the system function, which executes a shell command passed as an argument. The attacker also carefully crafts the data on the stack above the overwritten return address so that it looks like the correct arguments for the target function. For example, they might place a pointer to the string binsh, which they also might have injected somewhere controllable in memory, onto the stack where system would expect its argument. When the vulnerable function returns, it jumps to the legitimate system function in libstake system, then finds the pointer to binsh on the stack placed there by the attacker and executes it. Since system itself is legitimate code residing in an executable memory segment, the NX bit doesn't stop it. The attacker achieves code execution without injecting executable code onto the stack.
Wow, so they hijack existing code. Is there an even more advanced version? I think I saw ROP, return-oriented programming, mentioned.
Yes, ROP is the next level of sophistication, capable of bypassing NX and other defenses like ASLR, which we'll get to. The core idea of ROP is to find small sequences of existing instructions, gadgets, within the program's legitimate code or libraries that end with a return instruction. These gadgets might perform a small useful operation, like loading a value into a register, performing an arithmetic operation, or storing a value to memory. The attacker then carefully overwrites the stack not just with one return address, but with a whole chain of addresses. Each address points to the start of a chosen gadget. When the first read instruction from the vulnerable function executes, it pops the first gadget's address off the stack and jumps to it. That gadget executes its few instructions, and its final read instruction pops the next gadget's address off the stack and jumps there. This continues, chaining gadgets together. By carefully selecting and ordering these gadgets, the attacker can effectively stitch together arbitrary computations, essentially building a malicious program out of tiny pieces of existing legitimate code.
That sounds incredibly complex to build, but devastating if successful, like programming with tiny, scattered puzzle pieces. Given these sophisticated attacks, what are the main countermeasures against buffer overflows?
It's a multi-layer defense approach. 1. Non-executable memory, NXDEP. As discussed, marking stack and heap memory as non-executable is fundamental. It stops direct shellcode injection. 2. Secure programming practices. This is arguably the most important, preventing the vulnerability in the first place. Language choice. Using memory-safe languages like Java, Python, Rust
Go that perform automatic balance checking eliminates most buffer overflows by design. Secure libraries functions. When using languages like C, C++, might rigorously avoid dangerous functions like gets, stripest, strike-it, use safer alternatives like strine-chip, strine cat fic gets, or ideally modern C standards Annex K functions, strine, etc., or other libraries that require buffer sizes to be specified and respected. Perform manual bounds checking diligently. 3. Stack canaries, stack cookies. It's a runtime check. Before a function's return address on the stack, the compiler inserts a secret pseudo-random value, the canary. Just before the function returns, code inserted by the compiler checks if the canary value is still intact. If a buffer overflow has occurred and overwritten the stack up to the return address, it will almost certainly have corrupted the canary. If the check fails, the program aborts immediately, preventing the jump to a malicious address. It can potentially be bypassed if the attacker can somehow leak the canary value or overwrite specific bytes carefully. 4. Address-based layout randomization, ASLR. This is a powerful runtime defense against attacks that rely on knowing fixed addresses, like return to lib and ROP. ASLR randomizes the base addresses where the stack, heap, and shared libraries like lib are loaded into memory each time a program runs. This makes it extremely difficult for an attacker to predict the exact address of system or the necessary ROP gadgets, significantly hindering exploitation. They might have to guess, drastically reducing the probability of success.
So it's really a combination of better coding, runtime checks like canaries, and making memory unpredictable with ASLR and NX. A constant arms race, it seems. Hashtag tag outro.
Wow. We have covered an incredible amount of territory in this deep dive. We started right down at the foundations, seeing how the OS acts as that essential abstraction layer, hiding hardware complexity so even a simple print works seamlessly.
Yeah, and then we built up from there, looking at processes, these isolated containers for running programs, how the OS creates them with fork and copy on write, transforms them with execs, and manages their lifecycle right through to exit and wait.
We explored the intricate choreography of CPU scheduling, understanding the difference between CPU-bound and I/O-bound tasks, and seeing the evolution of algorithms from simple FCFS to round-robin, and finally to Linux's clever, completely fair scheduler, all trying to balance fairness and responsiveness.
And we saw how threads provide that lighter weight concurrency within a process, sharing memory but needing careful synchronization. We touched on user versus kernel threads and the trade-offs involved. Then we plunged into the thorny issues of communication and conflict. IPC mechanisms like shared memory and pipes, the nightmare of race conditions and shared data, and the crucial role of synchronization primitives, spin locks, mutexes, semaphores, trying to ensure mutual exclusion, progress, and bounded waiting.
And we faced the reality of deadlocks, those circular waits for resources, understanding the 4 necessary conditions and the different strategies for handling them, from prevention and avoidance to just detection and recovery, or even the ostrich approach.
Finally, we focused squarely on security, the OS as guardian. We looked at the goals, availability, confidentiality, integrity, and the mechanisms like discretionary and mandatory access control, DAC and MAC, with models like Bell-LaPadula and Biba trying to enforce policy.
And we ended by diving deep into a persistent, real-world threat, buffer overflows. Understanding how stack overflows work, the evolution of attacks from direct shellcode injection to return to lib and sophisticated return-oriented programming, and crucially, the layered defenses like NX, secure coding, stack canaries, and ASLR that systems use to fight back.
It's truly mind-boggling when you stop to think about all the invisible work the operating system is doing constantly. Every click, every window, every network packet, it's all orchestrated by this incredibly complex piece of software. Hopefully, understanding these mechanisms gives you a much richer appreciation for how your computer actually works and the constant innovation needed to keep it running smoothly and securely.
Absolutely. And maybe a final thought for you to chew on. As our systems get even more complex, with more cores, specialized hardware like AI chips, pervasive networking, how will these fundamental OS principles we discussed, process management, scheduling, memory management, security, need to adapt? Will we see radically new paradigms emerge, or will we continue to build upon and refine these core concepts that have served us so well? What are the next big challenges, the next clever solutions in this ongoing quest to manage complexity and secure our digital world?